So I would like to finish the series of 3 talks, and without skipping on my transparency, where is that? After uni, yes. Okay. So let's summarize. On the first day, I thought, isn't it too loud, I think? On the first day, I talked about the dynamical properties of geodesic laminations. And then yesterday, I talked more about the topological aspects of it, namely using these geodesic laminations with strange structures to analyze the tangent space of the space of all measured laminations, which is an object of interest to topologists. And today, I was talking a little about geometry and some applications of the machinery I constructed in the first 2 talks. Now, there are several things you can do. So this is just supposed to be a sample. So I'm just selecting one kind of problems which you can attack through this differential calculus on the space of measured laminations. And that's the problem of analyzing the geometry of 3-dimensional hyperbolic convex cores. So you start with a M 3-manifold with a hyperbolic metric, namely a complete metric of constant curvature -1. And the only interesting case here is when M is non-compact and actually has infinite volume. So I might as well put that in. And if you ever read the famous Thurston lecture notes, you probably encountered the convex core of M, which actually goes back to Nielsen in the case of dimension 2. And in a few words, it's the smallest non-empty convex subset, smallest closed non-empty convex subset of M. And it exists.
Carries pi1.
What?
Carries pi1.
Well, you know, if you put a good definition for convex, then that's enough. There are 2 definitions for convex, so use the good one, and then the next slide is going to be more precise. So, but intuitively, that's why you're interested in this one. And it exists, except in some degenerate cases, like the hyperbolic space, and it's unique. So it's something which, in general, is well defined. But the way you really want to consider this is by considering the limit set of the manifold. Namely, if you consider the universal covering of the manifold, it's a simply connected hyperbolic manifold and there is only one. So you can write your manifold M as the quotient of the hyperbolic free space under the action of some of the fundamental group M, some isometric actions, and then you define the limit set as a set. So that take the ball model for hyperbolic space, and then there is a thing called the limit set, which is something which sits on the boundary sphere, and it sits on the boundary at infinity of the hyperbolic space, and what that is the set of cluster points of any orbit. Again, it's except in some degenerate case, namely essentially when the fundamental group of M is abelian. There are very few of those. Okay, and then what you do, I know that Dave's talking that I should point on the transparency, but I'm more comfortable with this. What you do, so you have the limit set, which is green. It's a wild set, for instance. I mean, you've seen pictures where it's a Jordan curve, which is nowhere differentiable. And then you take the convex hull of that thing. Namely, whenever you take 2 points here, you draw the geodesic, and then so that gives you a set of geodesics, and then when you have to take 2 points on the geodesics, you take again the geodesics going through them, and so on. Actually, if you use the projective model for hyperbolic space, the Klein model, then it's exactly the Euclidean convex hull. So actually, it's not such a weird object. And by invariance of the limit set under the group action, this thing is invariant under the group action, and so when you project, you get something in M, and that's exactly what that convex, convex core is. The good thing about this is that this gives you some insight about the geometry of the boundary, because it's a convex hull. And if you remember, if in R3 you take finitely many points, if you look at what the complex hull of those look like, well, it's a polyhedron. And you know, a polyhedron, you have vertices, you have edges, and you have faces. Well, here you have exactly the same phenomenon. Locally, you have, well, let's begin with faces. You may have some flat pieces. So first of all, let me begin. First of all, topologically, you know that a convex set, locally it's a manifold with boundary. That's exactly what happens here. So topologically, it's a surface. And then it's a union of faces, namely flat pieces, which are totally geodesic. Edges, namely geodesics. And then vertices. But the vertices, you know, they are at infinity. So you don't see them in the quotient here. So actually there are no vertices. Right? So it's all the union of these two things here. I mean, take the proof of this fact for a compact convex hull in R3, and that's exactly the same proof. Okay, now something which is more tricky is that if you consider the path metric induced by the hyperbolic metric on this topological surface, then it's hyperbolic. Well, it's like if you take a Euclidean polyhedron, well, you know the metric is badly behaved at the vertices. The cone angle is wrong. The angle added up to less than 2 pi. However, on the face it's certainly nice, it's Euclidean metric. And then on the edges also, it's Euclidean. Well, here exactly you have the same behavior. So what do you have? You have a surface with a hyperbolic metric, and it's got these edges, namely these geodesics inside. Hey, that's a geodesic lamination. So you see that you have to think of this. You have a hyperbolic surface which bends along the edges, and these edges form this geodesic lamination, which is called the bending locus of the boundary. And then the next stage we want to ask is, how can I measure how much bending I have? So you can measure the bending, but it's 2 slides down later. And we're going to see that the bending is measured in this case by a transverse measure. So actually you end up with a measured geodesic lamination, and which is called the bending measured lamination of the boundary of the convex hull. There's supposed to be a boundary here. Okay. So this boundary of the convex hull, that's actually a special case of something else called a pleated surface. A pleated surface is essentially the same thing, except the boundary was convex. Here you don't require convexity anymore. So you say that a pleated surface, well, that consists of a map from a surface into M. What happened to M here? M. Such that F is a path metric isometry, namely that it sends each arc to an arc of the same length. And the second property is that there is a geodesic lamination lambda in that surface, called the pleating locus of the pleated surface, such that F sends each leaf of lambda to a geodesic of M, so F is straight on these geodesics, and totally geodesic on the complement, so flat outside of those. However, it bends, so exactly like in this case, except that it can bend up or down, so it can look like a wild thing going up. Now, one thing you have to remember is that this is a geodesic, the green stuff here is a geodesic lamination, so most likely this will be a counter, the set of corners here will be a counter set. That's exactly what happens here. So the situation is pretty wide, or can be pretty wide. And the question is now, for such a pleated surface, you can ask, how do I measure the bending? See, here already, I don't know, if you read Thurston notes many years ago, like many people in this room, you may remember that to show that there is a transverse measure, there is some kind of triangular inequality. I mean, it's which guarantees the converge, because you approximate by finite things, and then you look at the triangle, and then there is a certain inequality which guarantees that when you approximate by finite pieces, the process converges. Well, here you don't have this luxury anymore. But here was what we can do. So let's say that you look at the piece of the surface, and you want to see how much bending occurs here. And one way to do that is that just, instead of construing the piece, consider an arc transverse to the geodetic lamination. And that's what I like to do. And then you want to see how much bending occurs. Well, there are many ways of measuring the bending. Here is what's probably my favorite one. So might as well do that. So what's this picture? The problem is that not only you need to be a mathematician here, but you need to be an artist. I'm good at neither. So what this piece here is supposed to represent is the same thing as over there. And it's inside of the three manifold, and you have that piece of pleated surface. And then what you do is that, you have all these, probably easier to see it here. So first of all, you choose a direction. Let's go left, this way. And you draw all these geodesics, you extend them until they hit the sphere at infinity at this point here. And then whenever you have a face, when the face, you also extend it, and you see, and I give you, so you have a total geodesic wedge here, and so at infinity, it hits infinity along an arc, which is what's supposed to be represented here. Now, some of them give you points, by the way. It's when you have a wedge going this way, where the 2 points converge to the identity. But the ones which converge, which expand in that direction, when they hit infinity, they hit along the intersection of a totally geodesic piece, which is a circle. And so these are pieces of round circles. It doesn't look like it in the picture, but it should be. And then you want to see how much bending occurs there. Well, so there is one thing called Gauss-Bonnet, which enables you to do that. Because so this picture here, I redraw it here. So it's a picture on the sphere at infinity. I just put a magnifying glass. And what do I see? I see this curve here, which is made up of round circle arcs. And I want to see how much bending, how much the curve turns at the vertices. Now you remember, I have a counter set of vertices. If I only had finitely many points, that would be easy. At the isolated point, you just measure the R. 0, alpha. Eh? But if I have a counter set of bad points, that's difficult. So what you do is that you have this curve here. Well, you extend it by a smooth curve, anything. You choose whatever you want. Choose a smooth curve. Yeah.
What makes the plane curve embedded locally?
Oh, it's not. It's not. The wheel. No, actually, that's a good point. It will not be embedded. Yeah? I'm sorry. Yes. It's just like I don't know. My picture will be even worse. So no. In general, in particular, near, if you have a close geodesic, then actually you get you can get pretty pictures in that way. So it's not embedded, eh? And you connect the two ends by a smooth curve like this, and then you try to remember what the Gauss-Bonnet formula tells you. The Gauss-Bonnet formula tells you that when you integrate the curvature along a curve, if you have a closed curve, you look at the amount of turning along that curve, and then you integrate the curvature. It's equal to the integral of the curve, and if it bounds some surface A, it doesn't need to be embedded, then the Gauss-Bonnet tells you that this integral is equal to the integral of the curvature, which is the area enclosed, plus something which depends on the topology of the enclosed area, except that thing is 2 pi, the other characteristic, namely it's a multiple of 2 pi. And, it's pretty clear that the arcles, I will only be able to measure them modulo 2 pi anyway, so I might as well do everything modulo 2 pi. And if I consider the area minus the amount of curvature along the smooth piece, the only term which is left is the amount of turning at the corners. Okay, that would be for a curve made up of finitely many pieces, and for a general curve where I have a counter set of bad points, well, I can take this as a definition of the amount of turning occurring at the vertices. Okay, so that's, now you have to show that this converges, and guess what? We again have to use these estimates about the length of the gaps. So anyway, that guarantee, so you can show that you can define the amount of turning by this formula here. This is independent of the smooth curve, that's easy, and intuitively it does whatever you want. And also a property.
So how do you adjust the construction when it's not embedded? What do you say?
Same thing. So just like the area. A good point is that the area, it's the enclosed area of the sphere. It's only defined modulo 4 pi. But if it's defined modulo 4 pi, that's the area of the sphere, mind you. But if you define modulo 4 pi, in particular, it's well defined modulo 2 pi, and so you don't care.
I just don't.
Take any cycle. Take any cycle bounding that closed curve, and the area is well defined modulo 4 pi, and so you're fine.
No, but unless the curve has the signed area doesn't have meaning if the curve is very wild. You have to have a certain regularity on the curve.
Well, it's rectifiable. The curve is rectifiable.
Oh, it is rectifiable.
Yeah. So you're fine. No,
okay, I was worried.
No. It's not as wide as you might think. It can be wider than I draw it, but not that much. Okay, so and then it's pretty clear that this construction, I mean, if you sit down a little bit, you see easily that this construction is finitely additive in K. It's invariant as I move along the geodesic lamination, and so that defines what I call a transverse cosine, except that now it's not valued in R anymore. It's valued in the circle R mod 2 pi. And that's again the reason why there is the 2 pi that you don't expect angles to be defined in R. You just want the best you can hope is to have a defined modulo 2 pi. Okay, so this transverse cosine which measures how much you're bending up and down. That's the bending transverse cosine of the pleated surface, which also gives me a Helder distribution, transverse distribution, if you remember what I talked about in the previous two talks. Okay. Now, the point, once you've done that, here is the fact. When you have a pleated surface, I removed the definition, but the pleated surface, you had a hyperbolic metric on the surface, you had a geodesic lamination, and you had this thing which measured the bending. Well, you know, if you think about it, here is a surface with a boundary. If I take a bending locus like this, and if I know how much I'm bending, if I know the angles along each of the edges, well, I know the geometry of the surface. I have everything here. Okay? Well, here you have exactly the same thing. Now, of course, it's a little wider than this piece of paper with finitely many folds, but the fact is that from this data, these three data, you can reconstruct the geometry of the surface. Okay, and not only you can reconstruct the geometry of the surface, but you can also do that in the universal covering. Namely, you can take the universal covering of the surface, the universal covering of M, which is the same as hyperbolic space, and F tilde here. I should proofread that. Well, you're going to see that I wrote this extremely fast on Sunday, and I didn't proofread well enough. You have this lift, and you can construct the lift as well. And once you know the lift, this F tilde is equivariant with respect to a representation from the fundamental group of S into the fundamental group of M, which is a group of isometries of the hyperbolic space. So you get this representation here. So from this data, you get a representation here. Okay. Now the proof, if you're just bending in the convex way, well, the proof is relatively simple. I mean, there is that relatively famous paper of David Epstein and Al Marden, which really puts all the epsilons and perhaps even a few more in addition. But you're dealing with transverse measures. The convergence of those things are relatively easy. If in the general case, it's a little tougher because you have distributions which tend to be a little wider than measures. And this is proved, this idea of reconstructing the surface from these transverses in deformation, you can see it as, you can do it by something which is analogous to the gap formula. If you remember yesterday, the gap formula, that was that thing where you compute the integral of a function with respect, in terms of how much you jump over the gaps. And then you have a similar formula, but yesterday in the gap formula you were computing a real number. Here you want to compute, to determine an isometry telling me how much move this piece of the pleated lamination as I vary the cosine. It's tougher because the isometric group of H3 is non-commutative. That screws up everything a little bit. I mean, so it's a little more. Yeah.
Even though this thing has criteria, but it's very simple. So how do you do the left one?
I'm sorry?
And even though it has criteria by outputs, but the length is it?
The length of what?
Of your set.
No, the length of what?
That
This curve, no, the length of this curve is actually finite. That was Dennis's question. It's a rectifiable curve. You have to show that, but it's a wide curve, but it's rectifiable. So it's not as bad as you might think. And so you reconstruct. So the convergence is a little more tricky. It's not that bad. Every time you just have to bound things by the geometric series, but you have to do things in the correct order. That's the main problem.
Okay. Is there a problem going because you have circle coefficients? You go from the cocycle, the circle coefficients to the Holder distribution?
We're not there yet, but that will come. No, there is no problem.
No problem.
No problem. See, what happens is that one trick to make this define over R is that instead of considering a manifold, you consider a deformation, and you see how much things move. So instead of considering functions, you have closed forms. It's something physicists do all the time, and no problem. I mean, you don't have to worry about that. Okay, now you can get the converse, namely that you have this map to these three data you associate with representation. Well, I would like to use, to go conversely, what I want to do is understand the deformations of my three-dimensional hyperbolic matrix. Now, it's the same as understanding the representation into the asymptote of H3. So let's move a little bit the metric, which moves my representation. And assume in addition that lambda, the geodesic lamination is maximal. So maximal means maximal, that you cannot extend it to a larger geodesic lamination. And in practice, the way you see that the complement consists of infinite triangles. And you remember, S minus lambda hat, there was that thing with spikes. And sometimes you could have, in the picture I had given on the first day, you had a few triangles and one puncture torus. When you take the case where the puncture torus doesn't exist, namely that the complement, of course, is only of infinite triangles. What's good about triangles, let's see what's bad about squares. Well, let me go back. If you deform the representation, well, you are deforming the metric a little bit. That's the way you have to think of it. And if you think of that, if you deform the metric, well, you know that what used to be a geodesic becomes a quasi-geodesic, and so you still have a geodesic nearby. So actually, you can keep track of the geodesics. The only problem is that when you have a square in the complement, I don't know, it's a square like this, which was flat. When you deform the geodesic, we can deform them, but the square can become skewed. And so you see the bending locus increases. I don't want that. So I already put a diagonal, and then there is no problem, because the triangle is never skewed. So if you do that, when you deform if I deform my representation to one which is nearby, I can still find a new pleated surface which has the same pleating locus. It's this idea that you can still keep track of the geodesics, except which is equivariant with respect to rho prime instead of having it equivariant with respect to rho. Yeah, there I have it. Okay? So I have this picture here equivariant with respect to rho. Now, if I deform rho, I get the similar picture with primes. And then I can measure the hyperbolic metric on that new pleated surface and the bending of that new surface, which gives me an element transverse cocycle valued in the circle like this. And the proposition is that this gives me a local diffeomorphism, namely that the map which to a nearby representation associates the metric and the bending of the corresponding pleated surface give me a map from the space of representation of the fundamental group of S into the isolated group of H3 into the Teichner space times this space of transverse cocycle. And the claim is that this is a local diffeomorphism. Okay, now.
You smooth out the edges?
What?
You smooth out the edges?
What did I?
You smoothing out the edges?
No, I don't smooth anything. Everything is polyhedral. Now, this is probably impressive at this point, because what did we achieve? When we got the parametrization of the space of representation by this thing here, Teichner space, it's a nice manifold, well understood. This is even better. That's when I had R, that was a finite dimensional vector space with R over 2 pi z. It's the same. It's actually a disjoint union of two tori of the appropriate dimension. When you can compute that, it's easy. So this is also a nice manifold, and we have this local diffeomorphism. And what's good about this local diffeomorphism is that it's well behaved with respect to the geodesic lamination. So this is going to enable me to keep doing calculus.
Which representations are involved here?
The ones which can realize, the ones for which lambda is realizable. Whatever that means. Now, if you give me a geodesic lamination, you ask me for which ones it is realizable, I don't know. But at least it's
realizable as what?
By pleated surface.
Oh.
Which is equivalent with respect to the representation. Okay. So actually, that's the one. I said that the space of transverse cocycle is 2n to 1. Okay, so the application I have in mind is the following. I start with this hyperbolic metric, and I deform it, and I want to see how the geometry of the boundary of the convex core changes. Well, so first we have to understand how you can deform this. So there are a few keywords which either you know what they mean or they don't, but let's say under a relatively mild hypothesis, the space of deformations of M is a manifold, and the topology does not change. So what kind of mild hypothesis can you put? Well, it depends on your religion, but you can require M to be convex or compact, whatever that means, or something a little more general. You could take M geometrically finite and restrict to cups preserving deformations, or so that's a theorem of Almard which guarantees that the end of the sentence is correct. Or you could restrict to holomorphic deformation, that's the theorem of Dennis, which tells you that the conclusion is still hold. So under some, you have to put some hypothesis so that the situation is not too wide. I think here you're supposed to say the situation is structurally stable, that's what you say. Anyway, so under the hypothesis like this, the topology of the convex core does not change. And so the boundary of the convex core of the nearby metric has a natural topological identification with the one you started with. So let's call it S to make sure that, to understand that, to emphasize the fact that it does not depend on the metric. Okay, and if you look at the geometry of this guy, well, the geometry I said is described by a metric and a transverse foci, but because you're bending, it's convex, so you're bending always in the positive direction. And a cosine which is always positive, now you have to figure out what that means if it's not 2 pi. But, okay, let's not worry about that. If the bending is always positive, then that gives you a measured lamination. Okay, now let's consider D, the space of deformations of M, and deformations meaning with possibly restrictions of this type. And everything is designed so that this is a manifold, and so what do you get? To deformation, you get a hyperbolic metric on the boundary, which is a hyperbolic metric on this surface, so you get a map from the deformations to the space of hyperbolic metrics. And this is a manifold. Stationary space is a manifold. You can ask, is it differentiable? Well, that's a question you can ask. And the second one, the first question you can ask is it continuous, by the way? Even that is not trivial. And the second one is, to deformation, you can associate the bending of the boundary, and again, you can ask, is it differentiable in a weak sense? Okay, so that's my goal here. Try to show you what the machinery which we developed enables you to answer these kind of questions. And there is something proof because, you know, I mean, that's the whole point of the idea. There is this differentiable world of calculus which people have been using for the past 200 or 300 years, when was calculus invented. Well, there is a huge machinery there. On the other hand, in a very natural situation, like something which comes from simple closed curves on the surface, you have this piecewise linear manifold where there is no nice calculus there. So you want to merge these two things. And if you want to merge them, well, you know, usually the way mathematicians solve this kind of problem is by making definitions. And so what you do is that you want to notion definitions which have been around for a long time, actually, with the analysts. You want a notion of differentiability which is going to work in the classical case and in the piecewise linear case. So if so I'm going to introduce a weak notion of differentiability. If U is an open subset of Rn, and if I have a function phi from U to some Rn, I'm going to say that this curve is tangentiable. I mean, it has a tangent map. So if there exists a tangent map Tx of phi going from Rn, the tangent space here to the tangent space, such that, okay, you know how to understand the tangent map of differentiable map. Eh? What you do is that you give a point, you take a curve and a vector, to compute the image of the vector under the tangent map, you take a curve which starts at this point and is tangent to that vector, and then you transport it by the map phi, you get a curve arriving in Rn, and then you take the derivative of that. Eh? Okay, that's one way you can define the tangent map, and what's very mysterious in general for differentiable maps is that it's linear. But if you don't insist on linearity, you can take this as a definition of the tangent map, and that makes sense. And so I'm going to say that phi is tangentiable if it admits a tangent map like this everywhere. So, two key examples. Differentiable maps in the usual sense, and piecewise linear maps. I mean, there are other ones, but...
Do you think there's some notion in this is a little bit of a digression, but go with your philosophical remarks.
Yeah.
Do you think there is a replacement of linearity in this for general context?
I don't think so, because...
It's not linear, but I mean,
no.
replace the concept. So you're only replacing the directional derivative, correct? You want to replace the other part, too.
Yeah. Somehow it doesn't seem to be the case, but...
I think it's just a final topology.
What?
It's a final topology. It's the final one that we need in order to describe reality.
Yeah, I mean, it's a little reminiscent of what the analysts call Gateau differentiability. It's not exactly that. It's a little stronger. It's like a uniform Gateau. The key lemma is the following. If I have a local homomorphism, if phi happens to be a local homomorphism, well, it will happen, and if it has a tangent map at x, and if the tangent map is injective, then the inverse is tangentiable at phi of x. I mean, it's an inverse function theorem, but it's very simple because the fact that it's a local homomorphism to begin with simplifies your life. For instance, a very degree argument, it guarantees that this map here is also surjective. And then we just extract, there is another definition of this using just sequences converging and seeing in which direction they converge. And then you extract subsequence in all things. I mean, it's a five-line argument to prove it. It's very simple. Okay, but I'm going to use this easy criterion to show that the maps I'm interested in are differentiable in that weak sense. So here is the idea. So where am I? I'm considering the space of deformations on M, and the space of, and if I restrict to the surface, I get a deformation of the covering corresponding to the surface, and this is going to give me deformations of the representation of the monodromy representation from the fundamental group of the surface to the isometric group. And so we have this map here where deformation of M, representations, and then we go to from looking at the convex at the boundary, you get this hyperbolic metric and the bending of the boundary. Okay? So you have the map going this way, yeah? And you want to show that this map is differentiable in a weak sense. Well, the first map, this is a manifold, this is locally a manifold, and it's defined by restriction. I mean, since I didn't say what the deformation was, how that was a manifold, but standard techniques give you that this first map here is differentiable. So the only one thing I want to show is that this one is differentiable. And instead of showing that this one is differentiable, I want to look at the inverse. Okay? So first of all, so I'm interested in the second map, but I'm considering the other map where, starting from the hyperbolic metric and the bending, I reconstruct the representation. So I told you that this map exists. First, I'll show that this is a local homomorphism. This defines actually a projective structure on the surface. If you've heard of this work before. And so this is a local homomorphism, and so I'm planning to use this lemma here. I have a local homomorphism, and to use the lemma, what I need to know is that it's tangentiable, and that the inverse is injected. Okay, so actually I don't need this one anymore, because I repeated what my map is. So I have this map here, and I'm trying to show that it's tangentiable. So now we have an interesting phenomenon, which is, I'm going to use the previous machinery now, which is that I take a point in here, and I take a metric, and I take the bending measure lamination here. Now, we saw that the tangent space of the space of measure laminations here, last time we saw it's a union of faces where each face corresponds to a larger geodesic lamination? Well, so let's call it, so if I take a tangent vector, it's going to belong to one of these spaces, h of lambda r. And then it's going to be a geodesic lamination with a transverse cocycle. And now, when you have, you might as well assume that lambda is maximal. I mean, you can always increase it so that that's the case. And now we have a different map. Namely, if you fix lambda containing the support of beta, then you also have a map like this where you, starting with a metric, a geodesic lamination, and this transverse cocycle here, you reconstruct a pleated surface which is not convex anymore. See, the difference between these two maps is that here you have locally convex pleated surfaces. Here they are not convex, they go up and down. And the key technical lemma is that if I consider the first map here, and if I, so I'm in this space here, and if I move in the direction of a vector space, a tangent space, the space of metrics here, V, and a tangent space W here, which is in the phase corresponding to the geodesic lambda, then I can go either this way or this way here, because the tangent space of this is also h of lambda with coefficient in R. So these two spaces, that direction, the tangent space of the space of cocycle here is the same as the tangent space to the space of visual lamination. And the claim is that these two things here are tangent. Now you compute, and you estimate, and you make sure you number in the equation. It's the first time I've used, I had to number equations. I think I have a 15 or something. You have to control a certain growth rate and so on. So that's what you prove. So these two processes, this one and this one are tangent. And the good point is that here we have this wide linear context. It's hard to understand. But this is a differentiable manifold here. We understand this very well. In particular, the second one, it's a local diffeomorphism. So that tells you that the tangent map, is an isomorphism. Okay, and I told you that this tangent map here is the same as the tangent map of this one here, at least in the direction I'm interested in. So that guarantees that on a given phase, actually, the tangent map of this one here is injected. Now, of course, you have to see what happens if you take vectors going in two different phases. You have to compare them. But somehow, if the two things cross, if you have bending in one direction, you don't expect, if one of them is being bent this way, you don't expect that you have some bending occurring the other way. That's the idea. So you have to compare different phases. But it's relatively simple. Once you know that the derivative is injective on one phase, then you need to show that it's globally injective. So that proves that the tangent map of this thing here is injective. And so my lemma, this easy inverse function theorem, guarantees that its local inverse, namely this map, the map from here to there, is tangential. Okay, so the whole point is to mix piecewise linear and differentiable manifolds and to apply this easy inverse function theorem. Okay, so corollary, this one is tangentiable, this one was differentiable in the usual sense, so globally this one is tangentiable, and then if you restrict to each of the two factors here, then it's going to be tangentiable. Now, there is a plus here, so that shows you theorem 2, for instance, that the map from here to the second factor here has a weak derivative in that sense here. The first one, there is a plus, because not only this map here is injective, but because it comes from differential manifolds, it's linear. And if you think a little bit about it, that gives you that not only you have a tangent map here, which is linear, namely it's differentiable in the usual sense. Okay, so that's how you can prove this kind of results. And actually in this one, if you work a little harder, you can choose C1. You have this map between differentiable manifold here, it's C1. However, you work out more examples and you see that it's not C2. It's probably C1 alpha, but it doesn't seem to be worth the trouble to prove it. So for experts, the problem is when you have faces are in the non-generic spots where you have very flat faces. If the complement of the bending measure lamination consists of triangles, then it is C2. The problem is when you have more than triangles in the complement. Okay, so this was a typical example of the kind of problems you can attack by considering this PL calculus on the space of measured geodesic laminations.
So this is a global result? I mean, D is all the deformation for a certain time?
No, it's local. It's local. Otherwise, I'm not completely sure how you define D. I mean, no, assuming that something is differentiable, it's local.
No, but I mean, is something a homeomorphism too? Something is a homeomorphism, correct?
That's a conjecture that it's a local homomorphism.
What's the conjecture?
The conjecture is that these two maps are actually local homomorphisms.
Well, D, is the dimension of D?
Dimension of D is the same as the dimension of B, yes. They have the same dimension, and you have a smooth map, and you expect that map to be invertible, but well, it's not always the case.
T of S means the touching of that?
Yes, that's the touching several boundary, yes.
I thought
it's not
the
known.
dimension was twice that. The dimension of the representation seems to...
No, look, take a quasi-friction zone. The dimension is it's twice the Teichmann space.
Yeah.
Well, of the surface in the middle. But here, the Teichmann space of the boundary has two copies.
Oh, you mean that's the boundary.
Yeah, that's the same. Yeah. Okay. So I will mention that proof.
I thought you were deforming the pleated surface in the middle.
No. The pleated surface, deforming the pleated surface in the middle, that's what you do in the proof. That's what that phi lambda does. Okay, so this is a natural problem which you would be interested in. This one could look a little weird, but actually it has an application. Namely, if I take a deformation here, infinitesimal, if I take the tangent vectors here, this map is tangential, so I get a tangent vector here. And this tangent vector is, I can interpret it as a geodesic lamination with a transverse distribution. And then yesterday, I told you that when you have a geodesic lamination with a transverse distribution, so that's the image. So I have this tangent vector here to the space, to the tangent space here. And if it's a geodesic lamination with a transverse distribution, I told you yesterday that you can consider its length with respect to the metric. Okay, that's a number which you can consider. And it turns out that this length here is, as a geometric interpretation, as the derivative of the volume of V, namely that logarithmic function V. Okay. To a deformation here, you can associate the volume of the convex core. I mean, the volume of that convex thing, which looks like a polyhedron. And then, as you deform things, when the things change, the polyhedron changes. So you can consider the derivative of the volume, and the derivative of the volume is exactly equal to this length times 1/2. Now, if you're familiar with the Schläfli formula does exactly the same thing for finite polyhedra in the hyperbolic space. It expresses, as you deform the polyhedron, it expresses the derivative of the volume in terms of the length of the edges and the variation of the dihedral angles. Well, if you think about it, that's exactly analogous to this, and actually, that's an ingredient in the proof. The idea that you chop into the convex core into pieces and you apply the usual Schläfli formula and you make sure that everything converges and then you get that. Okay, I have like 5 minutes and I would like to do a little more topology to follow up on this idea of how you can connect topology and geometry.
Why isn't there a second term with the derivative of the length coming in? I mean, the volume is kind of length times angle. So you
That's why,
you get
that's why it's the length of the variation of the angle.
Yeah,
See,
but you
it's
differentiate
L,
a product, you differentiate L angle, you get DL times angle.
Schleffly, it's only L d alpha.
I know, but why? Why is there no DL times angle?
Well,
Curvature minus 1 at the limit.
What?
Curvature at the limit. Curvature has the inverse of the length.
I can hear it here, it's fine here. Okay, I would like to just, as a last funny thing to talk about, I would like to connect, what I'm going to do, is I'm going to connect this idea of three-dimensional rotational angles to the bending of a pleated surface. It's relatively simple, but I think it's interesting. So, when you are in actually a Riemannian manifold, and you have a closed geodesic, when you have the monodromy along that closed geodesic, you take a parallel vector field, and when you come back, you don't come back where you started. So in dimension 3, transversely in dimension 2, so the difference, you can see how much you rotated around, so you see, you start here, you stay parallel, and when you come back, you see how much you rotated. And that's the rotation angle associated to to that closed geodesic. So that's in R or 2 pi. But by the way, what happened here between the two transparencies is that, see, this is typed, and then here I had half an hour before taking my plane on Sunday. So that's why it becomes handwritten now.
Pretty soon the handwriting.
Okay. So you can extend that. So more generally, if you have a map at this point from S to N, there is this is purely topological data, then you're going to say that a geodesic lamination lambda is realizable, when in this country it's with a Z actually, I realize, if there exists a pleated surface which is homotopic to the original one, I mean the correct homotopy class, and such that lambda is contained in pleating locus. In other words, that pleated surface sends the leaves of lambda to geodesics in M. Okay, so let's call O of F, I already used R, so I can use it, for the space of measured laminations whose support is realizable in this sense. Okay. In a Thurston's analysis of hydraulic free manifold, it's a key ingredient. And it's open in the you can show it's open in the space of all measured laminations. And so there is a theorem which says that there is a continuous, this idea of rotation number for closed geodesic in M. First of all, a closed curve on S gives you a closed curve in M, and a closed curve in M gives you a closed geodesic in M, and gives you a rotation number. Well, this idea you can continuously extend it to all the space of all measured laminations. That means that there is a continuous function rot for rotation from the space of realizable laminations into R, such that for every single closed curve that corresponds to this idea over there, except that you can make it, there is a way where you can lift the mod 2 pi to R in a continuous way. And then the second thing is that's linear in the usual way, namely that if you take a measured lamination and you multiply the metric by a positive number, then you multiply the rot by the same positive number. That's why you need to get rid of the 2 pi actually. And you can always multiply a number by a positive number. However, a number defined into 2 pi, you cannot do that. So there are ways of doing that. It's not completely unique. You still have it's unique up to the choice of the 2 pi. But, okay. Now also, if the geodesic lamination is realized by a pleated surface, where you can also define a rotation number along that geodesic lamination, and if you have a transverse cosine, I can also define the rotation number along that. Now, how do you do that? you define everything like the way I define the length. You remember the length? The length, I chopped my geodesic lamination into small pieces, and then on each arc, I looked at the length, and I integrate with respect to the transverse measure. Here you do exactly the same thing, except that you chop your lamination into small pieces, and then you see how much rotation occurs along the small arcs. Now, to define that, when you put a connection, or I mean, there are various ways to do that. Differential geometers do that for a living. And then you integrate, and because everything is differentiable, not only you can integrate with respect to a measure, but you can integrate with respect to the distribution, and also the continuity is automatic. You don't have to worry about anything. It's just a matter of finding the correct definitions. No proof, no epsilons here. And again, exactly like the length function was differentiable, this one also is differentiable, namely that the rotation number, this rotation function on the space of measured laminations, well, it has a tangent map. That's, and what that tangent map is, if you interpret the tangent vector here as a geodesic lamination with transverse distribution, then this is just the rotation number of that. I mean, it's just by linearity, it's like the length, no problem. But the funny thing, so, okay, it's a generalization of that continuous, of that length function, and actually it's a dual to it in some sense, because you have a complex structure on the space of the isometric group of H3. Remember, it's PSL to C. And actually, this rotation number is essentially the length times I. So it's closely related. So it's not too surprising that you have very similar results. But the funny thing is, it's the topology which comes in there a little bit. Through what's known as first intersection numbers. Sometimes it's known as first symplectic form, except it's not always symplectic. So what's that? It's a very neat idea. If you have a homology class when you, in the appropriate dimension, well, if you have two homology classes, you can compute the algebraic intersection number. Maybe you put one in general position with respect to the other one, and then you count the intersection number plus or minus according to whether it's this way or this way. But to put a plus or a minus, you need to assign an orientation to your cycles. Well, Thurston's observation is that actually you don't know if they coincide. They actually you do not need to assign a sign. Because, so let's take alpha and beta, two transverse cosines valued in R. Sorry, if I don't put the coefficient, it's in R. And if you, so you have to think of those as multiplicities for the geodesic lamination. And then if you want to compare like this, so you fix one, that's the green one, and then you perturb the second one in a smooth way, in the C1 way, this way. And then I claim that to each intersection point, you can put a sign on it. Because let's say that on the first one, I chose orientation going this way. When the second one becomes oriented too, because it was a perturbation. So that gives me a plus sign, minus sign on this one. Now, if I reverse the orientation of the green one, well, I'm also going to have to reverse the orientation of the red one. So I reverse the orientation twice, the sign stays the same. Okay, it's a very neat idea which enables you to define an algebraic intersection number on this space here. And in spite of the fact that the geodesic lamination is not oriented, or orientable, you can still define this intersection number. It's a great idea. So it's a form, it's clearly bilinear. So remember, these are finite dimensional vector spaces. It's a bilinear, it's antisymmetric, clearly. An exercise for you, since ATM started the trend here, it's like it's non-degenerate if and only if, when you look at the complement, S minus lambda, you look at the ends, namely what you would like to call, you have these chains of geodesics with spikes. So it's if and only if each of these chains has an odd number of spikes. So in particular, I mean, in the generic case, you're going to have only triangles in the complement, and if you have only triangles, 3 is odd, so this is non-degenerate, and in that case, this is called Thurston's symplectic form. but it's not always.
What does H of lambda mean?
What?
What's H of lambda?
With coefficients in R. This is transverse co-cycles with coefficients in R. I'm sorry, I forgot. Yeah. Yes. Okay, so easy topology here. It's usually. And the fact is that this intersection number here connects the rotation and the bending. If I have a pleated surface here with pleating locus lambda, well, I can consider the bending cocycle, which is defined by 2 pi. Well, the theorem says that, and also I have this rotation function, which was in the previous slide. If I have a transverse cocycle for lambda, I can define its rotation, which you can see it. If it's a transverse measure, then it corresponds to the generalization of the rotation number along closed geodesic. And if it's a transverse distribution, that corresponds to the tangent mark to the previous one. Well, and so the thing says that this rotation number actually is just the intersection for first intersection form of alpha with the bending. So the intersection form connects the bending and the rotation. Okay, I think that's all I want to say here. Just to mention that I only touch a few things. For instance, this theory here is heavily complex. The complex geometry of PSL to C is in the background everywhere. I didn't touch that. And in particular, it took me a long time to realize that the real theory, in some sense, bending, that's the imaginary part of this complex theory. There is a real theory corresponding to shearing, this translating. And that theory was actually developed by Thurston in his paper on stretch maps. Now, stretch maps is something I've had on my bookshelves for a long, long time, which I tried to read. And I think it's Yai who drew my attention at some point that actually what I was doing was already in stretch maps. And then there, at some point in stretch maps, we have 4 lines which say something like, well, you can also complexify the situation, and there is a theory there. Okay, then it is. So the only thing is that Thurston has a dual view of everything. That's what's confused me a lot. Is that instead of considering transverse co-cycles, he considers the dual form for the intersection form. So okay, if it's non-degenerate here, it establishes an isomorphism between this space here and its dual. Well, Thurston does everything in the dual, so that's why I never realized that was the same thing. Once you realize that, that's it. Okay, I think that's it. Thank you. I have the last slide. People kept asking me about references, so I mean, the big references are this first one, which is probably everybody here has a copy of this. Then to understand this one, this paper by Henry Epstein Green is always very useful, as well as the little book by Casson and Blyler on Geodesic Laminations. There is also Harvard and Penner Harvard, sorry. And then there are 2 papers of mine, some of which are published, like the first 3 ones, and the last 2 ones will appear, but you can also get them on my webpage, which you just have to tip your head and you can get the advice. I mean, hey, go to the webpage of the math department at USC and then follow the link to my page. Okay, thank you.
Any questions?
Could you put the last slide up again?
No, because I can find it.
Maybe just summarize. So we have bending.
Bending, that's beta here, and rotating, that's rot here. And one is going to the other one through the person.
So what, can you just say what this theorem is saying, just the words.
Well, okay, something you probably know. If there is no bending,
Yeah.
there is no rotating. That's, I mean, you probably know, because you obviously have. Yeah? So now, what you do is that, along the examination, take any vector field which is orthogonal and which is smooth enough.
So we have a pleated surface.
Yeah, take a pleated surface, and take a vector field along the image of the examination, which is orthogonal, and is smooth. So you pick whatever. The bending, the rotating measures how much you move with respect to that, in some sense. I mean, and you correct that by how much the connection twists along that thing. Okay, that's one way to measure the rotating. The bending, when you can measure the angle of what you do is that you measure, you have this vector field which you use as an anchor to measure angles, and the bending is that you measure how much the flat piece is, what the angle of the flat piece with respect to these base vector fields are. Okay? Well, you see the two are related. Right? So when you start integrating, then you need to get that. I mean, it's not a good, I don't know if it's a good explanation, but it's actually, if I write it this way,
that last equation. What does that last equation mean? Some piece of
what does mean?
No, the picture of it. You were just trying to say it.
Yes. Well, I mean that.
There are two things that are crossing because you have some tau.
Yeah.
No, they're not crossing. They're two weights on the same thing, right? They're two different weights on the same thing. That's what tau measures, right? Alpha and beta are two different measures on the same.
Yes.
Same thing.
On the same thing. And
then, but the left-hand side doesn't have a beta. Oh, because there's only one.
that's the rotation. Yeah, the beta is defined by the geometry. The beta comes from the pleated surface. So beta describes the geometric situation.
Oh, I see.
More questions? Well, thank you again.